Hi, good morning everyone. This is the session 1 of the School of AI. Now, compared to the amount of time we spend in class, the video might be faster because in class we pause and we take questions, but don't worry, we are covering the same content here. Now, some preface, we have around 350 students in EVA now. These are split into 9 batches. Around 80% of them are from EIP group, which is a very rich set of people learning together and trying to help each other. And we are expecting them to help non-EIP students as well, because there's going to be some conceptual upgrade which is required from what you already know and what you are going to be learning in the EVA, and these EIP students have already gone through that. So initial 4-5 sessions might feel very similar to the EIP students as well, but as we move on from there, you're going to see the content is really new. In fact, all assignments and all the sessions is completely different from what you might have attended in the EIP session. Now, there are 9 batches in total: M6, which is Monday 6:30 a.m., W6, F6, Saturday 9, Saturday 11:15, and Saturday 1:30. Sunday 7, Sunday 9:15 a.m. and Sunday 11:30 a.m. Now, if you miss your class, you can attend any session, but we'll request you to stick to your sessions, because that is where the assignments get linked to. You will be given 7 days exactly from from which batch you actually belong from. So if you're missing your session, please make sure that you are aware of the fact that your deadline time might reduce, or it will still not increase, because your content will still get accessible to you only when your batch actually starts. Now, the School of AI has slightly different tenets as compared to other initiatives which we have taken, like EIP. Now, in School of AI, what we're trying to do is to build a very small version of what DeepMind and what OpenAI are doing right now, and in fact what Harvard and other universities are also doing right now. If you understand how they work, they teach students, they select the best of the students to become researchers, and these researchers teach students even better, and then that's how the cycle gets started, and that is what we're expecting here as well. We are hoping that you guys will be able to pick up what we are, the kind of content we are going through. We are going to pick up the research topic which we want to proceed on. Basically, we are expecting you guys to learn and then actually become one of the researchers at the School of AI and help teach other students as well. Now, once that cycle is set up, we are expecting that we'll be able to generate enough resources to have in-house good computing facilities, as well as great researchers who will really attract really good students. And that's how we feel that this can be a really good sustainable model. We are hoping to expand this to other cities as well, but right now we are going to be limited to Bangalore in the first phase. Now, this is phase 1. Phase 1 would mean that you are actually getting you're learning some of the topics which we have already predefined. This is going to be a 9-month course, around 120 hours. Phase 2 is going to be only available for those people who are keeping their scores above 50%, and in phase 2 you will be actually working on the research topics of your own choices. We will still have some advanced topics which we will cover in phase 2, which will help you pick up the research topics better, but the idea here is that you'll be able to pick up your own domain. You'll be able to pick your own domain, and we'll be able to help you in those specific domains. We're also going to be selecting top 5% of EVA students to actually become scholars. They will be paid scholarships here, and right now it's not going to be much. It's still going to be substantial, but we are hoping that by the time we hit our second cycle, we will be able to actually pay them as much as they would otherwise be getting from their own companies. So really, you can actually quit your job and become a researcher in some time to come in School of AI. Now, some of the administrative stuff, make sure you have a Google Colab account. Most of the assignments will be done on Google Colab. Make sure you have a GitHub account. You'll be sharing your GitHub. You'll be sharing a code through GitHub this time. In EIP, you had shared your Google Colab links, and those links would work sometimes. It may not work sometimes. There will be the loss of logs and will not be able to evaluate properly. So we're going to skip all of that. You're going to be doing assignments on Google Colab, and they will be updating the file on GitHub, so we can actually go on the GitHub repository and actually go through your code. Now, just make sure that you're sharing your GitHub code just with us. So you'll get an email address available on the LMS which you need to add as collaborator, so only we can view your file, and you can share your file with anyone else after the submission is over. So that is completely up to you. Now, on the LMS, please add your profile details like your name and your email address if possible, because most of the times when you're not registering properly, your name will come as a 16 digit or 24 digit numerical number, and it's very difficult to figure out who actually is submitting the assignment. Now, we will not be posting answers or other course related knowledge on Telegram. Telegram is right now acting like Twitter. There's a feed of like 100 plus messages every day, and it's very difficult to keep a track of what actually has happened. So we'll be actually moving all the discussions to the LMS forum, and that is where we'll request you to answer most of the questions, because that can become a very good repository for new students to come in and actually learn that, okay, this is how this particular question needs to be solved, or these are the concepts they need to be aware of. Now, every session ends with an assignment and an online quiz on the LMS. The idea here is that you need to have real hands-on expertise on these concepts. If you're not working on these concepts every week, then you'll actually miss working on them, you'll miss understanding them, and you'll not be able to build higher and deeper concepts on top of these. The idea for quiz is to make sure that you actually are aware of the concepts we discuss in the class. Sometimes quiz are going to be marked, sometimes they will not be marked, but you need to attend that. If you're not attending assignment or quiz, there's a negative marking, so please make sure you're actually doing that. Now, discussions on the forums are also monitored, which means that if you're helping someone else, you have additional bonus points. This is going to be really crucial. If, let's say, the cutoff for a particular assignment is 45, you have achieved 44 or more, but you've not got 45, but we see that you actually have been helping in past to you have been helping other students in the past, so that buffer actually can be used to gain extra marks in these kind of assignments. So please make sure that you're helping others. It's going to be helping you in the end. You need a minimum of 50% score in EVA. If you do not get 50%, you will not be getting the graduation certificate, and you will also not be able to move to the phase 2. Now, you will get participation certificate because this is a certification program, but you really need to understand what you're learning. If you're not, then really it's not going to be helping you. So please make sure that you have 50% score or more. Non-submission of any assignment or not taking part in quiz is awarded minus 30% score of that quiz or assignment. So please make sure you are attempting. Submitting the question, submitting just the questions as the code is not assignment submission. You have to make sure that you actually have attempted it, and there is a proof in your code that you actually tried to work on the assignment and the quiz. Now, deadlines for assignment and quizzes is hard, which means that the portal opens, the LMS portal opens for assignment submission and ends exactly at the time of what is mentioned there. So there's no manual intervention there. So it is going to be automatic. So please make sure you're submitting assignments much before the deadline. Most of the time, many students are going to be trying to submit assignments exactly just before the deadline, and the server may lag, and you might miss some internet connectivity on your end. So anything can happen, right? So please don't do that. For assignments which are hard, you will be provided soft deadlines. You will not be told that deadlines are soft, because as Indians, like, we take deadlines as not, we don't take deadlines very seriously. So we're going to tell you that there's a deadline X. If the assignment is hard, that deadline will be extended automatically. Final deadline will always be mentioned on the LMS. So please make sure that you have looked at the deadline on the LMS. Now, Extensive Vision AI program, here we have 40 plus sessions. Each session is 2 hours. So this is the kind of session you will be spending time 2 hours with me in the classroom. You will have Q&A, you'll go through the content which we are covering through, and this is where most of the basics will be covered. We have around 5 to 6 combined review sessions. This is for the tough assignments and projects. It can be attended online, so you don't have to travel for these kind of assignments or these kind of sessions. We are also calling for industry experts. This can also be attended online. These experts are going to be talking about how do we write research papers, how do we actually train a really complicated network, how do we optimize the network for deployment, and other topics. These are additional topics which are not directly covered in the course content which we have shared with you earlier. From mid-May, you can come to the School of AI, which is at building number 164, same lane. The idea here is that right now the classroom is there are a lot of people in the classroom right now, and we don't like that. We want the classroom to be airy. We want you to be able to stay at the session, stay at the session after the session ends to discuss with other students. Right now we have to hurry up because you may have to go, and we also have to start our office. So that's why we have moved the whole session, whole School of AI to another building. There you can actually, after the session ends, sit. You can actually book the session, book the classroom to discuss with your friends. You can do your own EVA based meetups and so on. So that is going to be something we are looking at. This is after 15th of May. We will be covering a tens of research papers and their implementation. Your submission, except first few, will also be in the paper format. Now, this is important because the paper submission and acceptance actually is really easy. Submission and acceptance to the great conferences like CVPR is very difficult. But unless you know how to write a paper and submit it, you'll not be able to submit anything. So that's what the idea is, that your assignments are actually going to be in the format where you are submitting assignment as if you're actually submitting a paper. Now, your code as well as documentation both are marked. You must have a README file on your GitHub where one can go through and understand what your code is all about. This is important because other students and other people across the globe are going to be looking at your code, and they really need to understand how you have written that particular part. And unless you We also believe that unless you actually train other people or help other people learn, you yourself will not be able to learn a lot. Now, EVA is predominantly vision, but some text is also covered in NLP part, where we are going to be covering RNN and LSTM topics. Now, having said that, the way vision works is that it's essentially a object detection or a pattern detection problem in some sort of image, which means that if you can actually convert your data, which is right now images for most of the classes for us, but let's say you're talking about sound, you might have heard of Google Duplex. Now, when you say hello, the word is first converted to a spectrogram, which is sort of an image, and on top of image we train a deep neural network to learn how the word hello looks like. Now, once you learn how the word hello looks like, you can learn many different variants. This is very similar to learning how, let's say, a dog looks like. Dog from front, dog from right, some skewed, sometimes it's a different breed, but the network can very confidently learn this how actually a dog looks like. And this is what we are doing in audio as well. So we are training the network in how the sound looks like for different kind of voices and pitches and tones and accents, and the network finally learns, okay, this is how the word looks like. And this is not it's not just this. There are other algorithms like CTC which work on top of these to make sure that the context is also linked. Sometimes you have to sometimes when the voice is not clear, you have to still guess what the person actually spoke about. So there CTC and other similar things can actually come in. Now, EVA is one of the most extensive program out there, and we're really proud about this fact. Most of the courses you see online or even in the classroom, you're going to see that the deep neural network module is just the last month or last few sessions of the whole course. And this course starts from deep learning. So we are very excited and we are very happy that you have actually joined the course, so we can actually train you and you can actually get better at it. You can add it back to the community, and then we can together train more people. So this is really very, very exciting for us. Now, EVA for the first few sessions, as I said, for EIP participants might feel very similar. This is because you actually have grilled yourself through first 6 weeks of EIP, and we have covered many concepts there, but the overlap will end after 4 sessions, and as we move forward, it will be slightly easier for you to gather more concepts, but you're going to see that we're introducing many different ways of analyzing, understanding and evaluating what actually we are working on. So I'll request you to use this time to build up your Python skills, help other non-EIP students as well. So let's get started. Now, generally there's an image here. For some reason it's not loading. So I generally like to start with this particular image. Now, if you have attempted EIP and you have got 45% accuracy in the assignment 4, I believe this is how you felt after the assignment. Now, that assignment was really, really hard. We have seen online that Stanford students were able to get 45. Those students were doing their courses for 6 long months, and in fact 3 months for machine learning, and before that they already had a lot of good idea of how these things actually might work out. They had training assistants and professors, assistant professors, their seniors to help them out. You guys really worked among yourself, so that is really great. The top accuracy in Stanford was around 46%. You guys have got 64. One person also got 65, but that is outside Google Colab, so we were not able to evaluate that. So this guy actually knows how to write a deep neural network. This guy understands if there's a problem, there's a solution, and how do you think about solution. This guy understands what is obsolete, where you should not spend time, and most importantly, this guy actually helped everyone in the EVA, and that is what helped him understand the concepts better. Because let's say you understand one concept, and if you train that particular concept to someone else, there's a possibility that someone else will come up with a new concept and tell you, hey, do you know about this particular topic? And you might not, and they might be able to help you learn better. So that is how this whole group is supposed to work. Now let's build the intuition of where actually all of this started, where the deep neural network actually started from. Now this is a brain. You already have seen this in many images. One thing I wanted to notice here is that look at how the neurons are firing. They're firing outwards in. And the reason for that is that the actual processing in a brain happens on the outer periphery of your brain. Now, brain is actually like a sheet of paper. You can unroll it and you can unfold it, and you can see that it's actually a big sheet of paper, and it's crumbled, and that is how the shape looks like. That is how this shape looks like. Now, when the processing happens on the outer periphery, these signals, which in our language would be embeddings, actually go inside the brain, and there are other parts of the brain which will evaluate and which will combine these different deep neural networks together and then make a call. For example, a cat might be getting processed at the back of the head. The color of the cat might be getting processed somewhere near that particular region. If it is your cat, then you want to be doing face recognition for the cat. That happens in a different area. So all of these guys fire together, and finally you're able to say, hey, this is my cat. So this is very interesting. This is something which actually has contributed a lot to the deep neural network architecture which we are going to be learning. Now we are based on, so EVA is based on vision, so you're going to be using a lot of images, but what you see right now is not useful for us a lot, because here this is actually the muscle which is pushing or pulling or contracting the lens, which is allowing us to focus exactly at that area we are interested in. But this is the image which is important for us. This is the retina. When the light actually hits the retina, it actually is captured by the rods and cones. Now, rods and cones serve different purposes. One set is responsible for capturing color in a good lighting condition. The other set is responsible for capturing the black and white light, essentially just the intensity of the light. So you only have one channel there. Now, when we're talking about channel, I just want you to think that right now when you're looking at this video, you're looking at three channels, R and G and B. The color is shown to you. There are only three in nature, and that's all we have in these channels. We do not have any other information. So we have the red channel where all the red color is going to be there. We have the green channel where only green color is going to be there, and then we have blue channel where only blue color is going to be there. But let's say this photograph which you're looking at is an image. If this was an image painted by a painter, then he could have decided to directly use the color you're seeing. Now if you count, there might be let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 or maybe 15 different colors. So he can actually use 15 colors to make this, and it will look exactly the same. You will not feel any difference. So in that case, we have used 15 channels. Why channels? Because one single component or one single feature which is found a lot, and you can containerize it and give it a name like red, green, blue, purple, that becomes a channel. We are going to be talking about channel a lot today, so don't worry on that. Now, if this image was actually printed on a newspaper, then how many channels would you think it will have? On a newspaper, we actually have 4 channels. If you've seen the bottom of the newspaper, you're going to be seeing 4 different colors. Those are C, M, Y, K. Now, that is very interesting, and that is something you need to think on. Your phone has 3 channels. The LCD you're looking at, it has 3 channels. Newspaper has 4 channels. A painter might use 12 or 15 different colors. There are other kind of imaging where we actually have 12 channels as well. So you can actually divide one image into as many channels as you want, but it will still look the same. And that is very interesting. As long as you can actually combine these channels in such a way that you are able to get the original image back, you're good. And that is very important for us. The reason for that is because we are going to be taking our image and we're going to be dividing into many number of channels. Now in our case, we are not going to be focusing just on color. Maybe color, in fact, is just going to be a very small component of the kind of channels we are going to be looking at. But let's build it up from here. So the topic or the understanding I wanted to carry out from here is that one image can be divided into many different channels. Now look at this animation. This is our eye. Light falls on top of our eye, and in this case we are dividing that image into 4 different channels, right? So we have 4 different colors here. Now this is not what happens in our eyes. Our eyes have 3 color sensors, but those are not RGB. You just need to think on that our eyes do not have RGB sensors. Our eyes actually have these kind of sensors. We have blue, we have greenish, and we have this yellow actually. We don't have a red sensor. So you see that still now you have been looking at the colors and everyone told you that there's only RGB, but right now I'm telling you that there are many more different combinations of colors which can be combined together to look at any color or build any color. Now I'm sure that you might not have ever felt that your eyes are not able to look at a particular color, because our eyes can compose any color, and that is very crucial for us and for the understanding of what we're talking about, because here we have B, G and yellow. In case of honeybees, they have 4 sensors. So there are in some cases there's genetic mutation also in humans where they can actually see 4 different colors. So they have a very different depth. They are able to see ultraviolet as well. But right now the thing I want to take you from here is that we are looking at B and G and yellow, not R, and we can still see all the colors. So we can actually take any image and we can divide it into as many channels as we want. The only catch here is that we should be able to represent the same image back. And that is easy actually, that is not very difficult to do. So the things I want you to remember is channels. Now when you're looking at this particular photograph, what is this? This is pulao, vegetable pulao. Now when you're looking at these image, I want you to think in terms of channels. Now what are the channels here? The channels here are these. We have peas, we have rice, we have some bay leaves, cloves and some other ingredients. So whenever you're looking at any combination of image or combination of object, it can be something else which we are going to be covering soon. In this case we are looking at food, so I want you to think of food not in terms of what it actually looks like, but in terms of ingredients. And without those ingredients you cannot make the food. But once you combine all the ingredients, you actually get the food. Now the P here is a sort of a feature extractor which we are going to be covering soon. Now one P is just one P, but a collection of all the P becomes the P channel, right? Collection of all the red becomes the red channel. Collection of all the green becomes the green channel, and so on. So you have rice here, and when we combine all the rice and just the rice, it becomes the rice channel. So these are the fundamental channels of the product we are looking at, of the food item we are looking at. Now, if you listen to this song, you're going to be, this is a very beautiful song, recently came out. When you listen to this song, you're just going to be listening to the song. But again, based on our context, what we're talking about, I want to divide this song into these guys. I want to think that it's just not one single song, but it's actually is built up by people who are playing guitar, people who are actually playing piano, people who might be playing bass, people who someone who might actually be playing drums, and the guy who's actually singing the song. These are the channels for us, right? So we have divided our the information coming to us into different containers, and all of them actually can work on its own, and that is important. We should be able to extract just the drumming beat. We should be able to extract just the vocals. We should be able to extract just the piano component. We should be able to extract just the bass component. If you're able to extract that, and if you're able to match it back, then you actually get the channel. And that is how songs are also made, right? You have different people playing different instruments, and the recording is stored and then it's combined, and sometimes their recordings are also changed based on the requirements. So that is post-processing. So you are able to do post-processing. Now, when you're looking at these words, I want you to look at the characters which are used here. For example, look at E. We have E here, we have E here, we have here, 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 and other places as well. Now, if we talk about all the E's combined together, that becomes one channel for us. So what is the maximum number of channels which will be used for these kind of images? It's 24, because we have 24. How many characters you think will be used to build something like this? Or how many channels will be used to build something like this? That's 26, because we have 26 characters in our English language. Now, again, don't look at the person, look at the television. When you look at the television, what actually are you seeing? I again want you to divide all the information coming in. Now, that information will be in this kind of pattern. Like, we have many applications, we might have channels like Times Now here. Now, for example, let's talk about Republic TV. Now, on Republic TV, you find Arnab Goswami, right? You don't find Arnab Goswami screaming loud on Discovery Channel that maybe he's screaming loud to a tiger who might have just killed a prey, that the nation wants to know that why have you killed that particular. So you don't expect that, and that is not how things work. Every specific channel has its own usage. For example, Star Sports used to show all the sports competitions and games. Now, when you go to, let's say, Zee Cinema, you'll be expecting movies there. When you go to Discovery Channel, you're expecting documentaries and animal and technology related videos, right? So that is how we containerize the information. So what are we taking out from here? The information we are taking out from the concept we are taking out from here is the concept of channels. That you have channels, and those channels are expected to contain a similar information. The reason I'm using the word similar is because initially when we build channels, they are going to be containing exactly the same information we are expecting them to. For example, all the vertical lines, all the red colors, and so on. But later on, as we build complex channels, we are going to be collecting these together to make something which is contextually sensitive or contextually linked to each other. For example, if you are making an arc is built by many small edges. So we are going to be combining many edges, and then we are going to be making an arc. Now, arc is not a fundamental channel, because that arc might not exist anywhere, but that arc can be made by a lot of vertical and horizontal and angle line combined together. So that is the idea. We're going to be building very basic channels in our networks, and once those channels are done, we are going to be building complex channels through them. But what I wanted to take out from here is the concept of channels. This is a very important concept. So there are two concepts which we are covering today. One is channels, and others the number of layers. Kernels is something we are going to be covering in the next session. But kernel essentially is this 1P. So if you take 1P and ask your Pilau how many P's are there, then you can combine all the P's in a bowl, and that becomes a channel, right? So kernel is a feature extractor. Kernel is also called a 3x3 matrix. It is also called a filter, and there are many other names as well. So don't get confused. So kernel, feature extractor, filter, 3x3 matrix, all are same. Now, this is one of my favorite experiments because that helps explain how the deep neural network scientists came about and how they were able to build their concepts on top of what we're discussing today. Now, we need two board cats for these experiments. Now, these experiments are not called board cats, so if you search online, you'll not find these experiments, but these experiments are real. We make them sign Facebook-like agreement because everyone just says okay to that. No one reads what exactly is there in the Facebook agreement, and that's what we want to do with these cats as well. So this is the first cat we take. Look how cute she is. Yeah, you're doomed, baby, don't worry. And look at the second cat. she's very focused. She's just damn focused. She has some objective, like she's going to kill you, or she's thinking that why have you stolen her food, like so. Okay, now coming back to the experiment. Now we take the first cat, we take her head, we lock her head on a table so she can't move. Then we basically tie her eyes with a ribbon so she can't see as well. Then we inject her with radioactive glucose. Then we show her a screen, and as soon as we take the ribbon off, she sees the screen and the cat is killed. Now this experiment was done way back in 1940s and 50s, and at that time we did not have CT scans, so we can't see inside the brain. So there had to be some other way to figure out what exactly happens inside the brain. So when the cat sees a particular image, we want to know exactly how the brain is going to be using the glucose there, and that glucose is radioactive, so we can actually take a print of what actually has happened inside the brain. Now you might be surprised to know that if you already don't know about it, this is the image which was shown to the cat. This left half you see came out in the right part of the brain of the cat, and this is what got printed on the brain. This is very, very important. The reason for this being a very important concept is because if you do not know this is how our brain works, you just think that you look at something and you just are done with that. We have never given a thought at what actually happens inside a brain. Now when you're looking at a screen right now in front of you, that screen is getting printed on the back of your head, and that is very, very important and interesting for us also. Now this gets linked to the second experiment, but if you understand what has happened here is that we have taken a digital copy in our brain. You can call it an analog copy in our brain, but this is very similar to what we do in our image recognition algorithms or DNNs, where we take a digital copy, and that is where everything starts from. In case of eyes as well, what you're seeing, what may be dynamic, it may be moving in time, but not inside your brain. Inside your brain, it first gets printed, and after that some processing happens on top of that. Now you remember that we had the second cat as well. So through the second cat, what we did on the same setup, we locked her head, but instead of injecting her with radioactive glucose this time, we actually just took a small saw, the rotating saw you might have seen. We opened her skull up, so we have access to the brain, and then we attach our electrodes to these areas. We knew what part of the brain is going to be printed or what part of the brain, and that is where we added electrodes. We wanted to see what actually happens there. Now when we show her a particular edge, only that particular neuron fires which is responsible to detect that particular edge, and that is very, very interesting. That means that our brain actually has these kind of edge detectors, and that is the first layer of our brain. So when you're seeing anything, the first thing our brain does is to print it, and after printing, it tries and figure out where are all the vertical edges printed on the brain, where are all the horizontal edges printed on the brain, where are all the slightly angled edges printed on the brain, and so on. This is how we create channels in the brain. So these are already predefined by nature through millions of years of nature's research. But in our case, we are going to be asking a computer that, okay, I want 32 different vertical edges, or I want 32 different kind of edges and gradients. So we're going to be talking about that in a moment. But this is the second experiment. Now, if you stitch both the experiments, what happens here? We have a photograph, we take a printout, and in our brain, we actually, in these particular regions, we try and figure out this is a horizontal edge or a vertical edge, whether the edge is there at all or not, and so on. And this further gets connected to different complex channels in the next layer in our brain, and there we figure out, okay, you are actually making an arc, and that arc happens to have two specific colors, and later on we combine these arcs together in a circle, and that is how we recognize that we are actually looking at a circle. Now, look at this image. Now in this image we have applied one algorithm called Laplacian. These algorithms are available in OpenCV, but look at the bottom two images. This is Sobel X and this is Sobel Y. In this case we are just getting all the vertical edges, right? So you can actually extract all the vertical edges. These algorithms are already there. People have been using these algorithms since 1950s, and till 2012 they were the state of art, and after that deep neural network has come in. This is Sobel Y. You're only seeing the Y edges or the horizontal edges here. So you can write your own edge detectors, and this is you writing a edge detector manually. In deep neural network we ask a network to do this for us. Now in this image we have vertical and horizontal edges, but there might be a scenario where you instead of getting vertical and horizontal edges, you want lines at a specific angle. In that case, we will not want scientists, or in fact us as engineers, to sit and figure out what those angles are. We will ask a deep neural network to do that for us, and our deep neural network will only get those lines which are relevant based on a data set. So the connection here to remember is that we can make complex things from very small features. This is a very complex image. We have 3 here, we have 1, we have 7, there are arcs, there are some noise up here also, but we can build all of that just by using very simple features, and that is very, very important for us. So in our course, what you're going to see that we have image. The first thing we are going to be asking is that how can we divide this image into multiple channels, and we are going to be saying that maybe I need 32 or 64. Exactly how many channels we need, we are going to be discussing in the next session. But once we say that we want these channels, our deep neural network is expected to get back to us with these channels. network is going to figure out the best channel in which it wants to divide the image so that the loss can be less and the accuracy can actually increase. Now, this is how our brain works. When we see image through our eyes, the first thing is that it is actually transported to the back of the head. From the back of the head, we have 4 layers, and these are the layers where the processing actually happens. Now, if you are in EIP, you might have seen that we have actually created like 50 layers or more, but in our brain there are only 4 layers. Our brain is far more wider as compared to the widest network you might have ever thought of or even written on. Now, the connection here to remember is that more features divided into multiple channels. This is again same as what we said here, that we want our image to be divided into as many features as possible, and those channels and those features when combined together are going to be called channels, and these are multiple channels. So if you have, let's say, 47 features, you will have 47 channels. Now, I want you to listen to this music at your when you get some time. What you're going to hear is, first you will have the Windows song popping up, and once the Windows song is there, you're going to be listening to the 4 notes which are used to make that particular sound. Now, if you have never played a piano, that is how you are going to play a piano, without any intonation, without any pause, without any softness of touching the keys and a lot of different things. But when we actually convolve using those notes on the music, you're going to see that we can actually extract how that particular note was played. And that is exactly what we want to do in our deep neural network as well. If there is a vertical edge, we want to know how that vertical edge was used throughout the image. Now, let's think about a calculator, a very simple calculator. In a calculator, how many different kind of edges we need to write all the text there? It is just 2. One small horizontal bar and one small vertical bar. You can place them wherever you want, and you can make 1, 2, 3, 4 and all the digits we see on the calculator. And that is important. Now, the reason this is important, because now if I tell you that I've run my deep neural network on the calculator, a very simple one, and it is telling me that I have one large vertical line and one small vertical line. Now, when you think about this, we have already ruled out many digits. We have ruled out 2 because it has 2 short vertical lines. We have ruled out 1 because it has only 1 vertical line. We have ruled out 3 because it has only 1 vertical line, and so on. And we have pinpointed our expectation to few digits like 4 or 6 or 7 and so on, and 9 as well, right? 0 is of course ruled out because in that case we'll have 2 vertical lines. So we have already limited our final prediction to these 4. After that, we're going to be looking at what our horizontal edges are, and based on these features we can finally pinpoint, okay, I was actually talking about 4. Now, so the connection here to remember is that feature extractor, those vertical lines we're talking about, small vertical lines, is a kernel. It is also called a feature extractor. The P we saw in the Pulao is the feature extractor or the kernel or a 3x3 matrix for us. And once we extract all the P's or all the vertical lines from the image, what are we making is a channel. So a channel is a bag of similar features. If you have 47 kernels, you're going to get 47 channels. If you have 58 kernels, you're going to get 58 channels. Okay. Now let's get back to neural computing. Now look at this image. On the bottom we have edges and gradients. These edges and gradients are combined to make these parts of objects, and from these parts of objects we are making these objects. Now when we look at English, we have 26 alphabets, and we combine these alphabets to make words. Then we combine these words to make sentences. Then we combine these sentences to make essays, and from essays we make Game of Thrones or other stories, right? You can have really infinite number of stories, but all of that boils down to just these 26 characters. And that is crucial here, because as in language we say we from alphabets we make words, from words we make sentences, from sentences we make essays, from essays we make stories. In vision we are going to say from edges and gradients we are going to be making textures, from textures we are going to be making patterns, from patterns we are going to be making parts of objects, and from parts of objects we are going to be making objects. And if you combine objects, we can actually talk about scene as well, but that is for later on. And this is very, very important, because this is related to the question how many layers my deep neural network should have, as well as where should I add some different layers, max pooling and other sort, which we're going to be talking about right now. But you need to remember this. We're going to be asking you 100 times or more than 100 times again and again in the classroom, that first we start from edges and gradients, then we build textures, then we build patterns, then we build parts of objects, then we build objects, and from objects we build scenes. It's a very, very important concept to remember. Now let's talk about convolution. Convolution is the one core principle or fundamental operation you're going to be performing in the deep neural network. Without convolution, deep neural network will not exist as it does today. So this is a very, very important concept to understand. Now, when we spoke about English, we had 26 alphabets. We had A, B, C, D, E, F, G, H, and so on. In this case, we have these edges. These are the building blocks of vision. When you run your deep neural network or you train your deep neural network on a natural image data set, you're going to be getting these kernels always, and that is very interesting. So you train a new network and you train it from scratch again, you're again going to be getting these kernels. So this is very, very interesting, which means that our image always gets divided into some basic building blocks. Now some kernels like this one and this one, you don't have a lot of data here, right? And the reason for that, in fact these kernels as well, reason for that is that we need to give an expectation to our network. We need to tell the network that, okay, I want 64 kernels or I want 28 kernels. It is up to the neural network to figure out that it wants to use all those kernels or not. But we have to give it enough space. If you're not providing enough kernel, or if you're not providing enough number of possible kernels, then it's quite possible that the network might wanted more number of kernels, but because you have not provided allocation for those, that it is going to be using less, your accuracy is going to be slightly less. So we are going to be talking about how do we arrive at these numbers later on, but that's the idea. These are our ABCDs of deep neural network. Now again, from edges and gradients we make textures, then we make parts of objects, and then we make objects, right? It's very important. So edges and gradients, textures, patterns, parts of objects, and objects. Please remember that. In this case, same thing is happening. We have low level features, which is edges and gradients, then we have mid level features where we are making textures and patterns. From there we are going to be making parts of objects, and from parts of objects we are going to be predicting what exactly we looked at. Now before we proceed, I wanted to just click on this particular link. When you click on this link, you're going to be opening this specific page, which is this one. Yeah. Now on that page, I just wanted to write some character, let's say some digit. Let's say we write 6. Let me just reload the page. So when you get time, just click on this particular link and play around with this specific page. On this specific page, when you write some digit here, then you're going to see that how our deep neural network is actually using kernel and channel concept to break the image into different images, and then from there it is proceeding and trying to predict something more. Now I'm going to be writing one digit here. Let's say we write 6 here. Right, so in this case you're going to see that our image is 6 here. Our image is then divided into different smaller channels. These are slightly smaller, maybe same as well. We are going to see whether the size changes or not later on. But these are the 6 kernels which were used to design these 6 channels. You're looking at channels, you're not looking at the kernels. Kernels are going to be very small. They're going to be say 3x3 in size. But what they give out is going to be a large channel, which is going to be containing all the information which is required to get this image back. Now from there we proceed and do something else, but right now just wanted to focus on the first channel itself, the first collection of channels. This is the first layer. Now let's look at the core concept, the convolution concept. Now in this case you're looking at a 4x4 image. The purple pixels you see here is a 4x4 image for us. This is the input channel. On top of that you're seeing this gray dark purple channel, dark purple kernel. You see this 3x3 matrix which is moving all across. Now when you're looking at this image, I wanted to imagine that these are some numbers, these are some pixel numbers between 0 and 1. If it is the image, it's going to be between 0 and 255, but in case of deep neural network it may be between -1 and 1. If we have done some activation, that's going to be 0 and 1. We'll know what activation is later on, but right now just imagine it's just some sort of sequence of number. Now when our kernel is moving on top of this particular image, and in fact whenever it is stopping, it is actually doing 9 multiplications. Now whenever it is stopping on 9 pixels, it is looking at those 9 pixels on the bottom and is multiplying its own pixel value with the pixel value just below it. So you have 9 multiplications happening whenever it is stopping. Those 9 numbers are then combined and then sent to the next channel. So this 2x2 is actually the output channel. So this is the input channel, this is the output channel. The input channel size is 4x4. The kernel which is convolving on top of that is 3x3. And the output we get is 2x2. So it's a very important concept to remember. Now let's look at how 5x5 looks like. This is a 5x5 image, and on top of that we have a 3x3 kernel convolving. Now every time it convolves, we are again doing 9 multiplications and summing the value here. This is the output channel for us. Now I want to notice one thing. Our kernel is not going outside the image. Now if you are not sure how it might go outside the image, we can actually just say that we have some zeros here and can go outside. Why is it required, or why do we even have this concept? We're going to be touching on this later on, but I just want you to notice this, that it is not going outside the image. Also it is covering every pixel. It is this is the first pixel and this is the second pixel. sorry, this is the second pixel, right? It is not jumping from this pixel to that pixel, which can happen. This thing is called stride. So in our course, we are never going to be using a stride of more than 1. Right now, you're looking at a stride of 1. We will never be doing a stride of 2. Why does it exist? Again, concept for later on, but I'm telling you all of this because you might go online and see that there's something called padding, which is adding zeros all across the image, and we have a stride as well. When you're writing code or copying code, those values might have some numbers. I want you to make sure that you know what those numbers are and what numbers are we going to be using in this particular course. In fact, there's a heavy penalty if you're going to be using padding and if you're going to be using stride of more than 1. Now, we always use a 3x3 kernel. There are many reasons for that. Now, one of the biggest reasons for using 3x3 is that it is heavily optimized now. But before arriving at 3x3, we were using 7x7, we were using 5x5, we had 21x21 as well. Notice these numbers, these are odd numbers. So we generally try not to go ahead with even numbers. And reason for that is, in even, we do not have the concept of middle. If you do not have a concept of middle, you cannot talk about things on left and things on right. It is very difficult to create anything which is symmetric using a 4x4, for example. Can you create a triangle in a 4x4 without losing out on the pixels? Let's say if you have to use all the pixels effectively, you will not be able to do that. If you want to make a triangle in a 4x4, you'll still end up using the odd number of pixels there. You might be using 3x3 there, and that is why these things are important, because increase of a 4x4 has 16 numbers, a 3x3 has 9 numbers. So moving from 3x3 to 4x4, you're adding additional 7 numbers, and we are going to be talking about using millions of kernels. So that is literally a lot of space which is going to be wasted. So we need to have odd numbers. Now, because we have odd numbers, so we had sequence of 3, 5, 7, 9 and so on used early on. Later on, everyone is just using 3x3, and there is a very specific reason for that. Now, before we cover that reason, I want you to just understand this concept called receptive field. Now, this image you're seeing on the left is 5x5, as we've seen earlier. We have a 3x3 kernel convolving on top. Now, whenever we have a 3x3 kernel convolving on 5x5, we're going to be getting 3x3. Whenever we have a 3x3 kernel convolving on 4x4, we're going to be getting 2x2. That means that if our kernel is convolving on 49x49, we're going to be getting 47x47, and that is the idea, that whenever you are convolving on a layer, you're going to be reducing 2 pixels on the x-axis and 2 pixels on the y-axis, and we are going to be building something on top of that. Just remember that particular part. Now, so here we are convolving on 5x5 by 3x3, and we're getting 3x3. If we are convolving on 5x5 by 3x3, we get 3x3. If we convolve on 4x4 by 3x3, we get 2x2. And if we convolve on 3x3 by 3x3, we are going to be just getting 1x1. So this is important here. And the reason this is important is because if you convolve on 3x3 by 3x3, we are going to be getting 1x1, which means if we convolve on 5x5 by a 5x5 kernel, we will again get 1x1, which effectively means that if I'm using my 3x3 twice, these are not the same kernels by the way. If I'm using a 3x3 here and I'm using another 3x3 here, I'm going to be getting 1x1, which means using 3x3 2 times is equivalent to 5x5. Now in a 5x5, we will have 25 parameters. In 3x3, I have 9 parameters. Using them twice is 18 parameters. So instead of 25 parameters, you're going to be just using 18 parameters. Now let's say the kernel size we wanted is 11x11, and there are networks written before 2012 where we had 21x21 kernels as well. So if you want to get a 21x21 kernel, you'll be using 3x3 how many times? So there's a very easy way to do that. So from 1x1, we go back to 3x3, we go back to 5x5, then we go back to 7x7, then 9x9, then 11x11, 13x13, 15x15, 17x17, 19x19 and 21x21. So here we have covered 21, 19, 17, 15, 13, 11, 9, 7, 5, 3 and then 1. We have added 10 layers here, and each layer, let's say we have 3x3, so 3x3 is 9 into 10 is 90. So we have used 90 parameters, but if you're going to be using 21x21 kernels, you're going to be using more than 400 parameters, right? And that's the idea, that this allows us to reduce the number of parameters. Now, because we started using 3x3s, NVIDIA and Intel and other graphic card manufacturers have made sure that 3x3 is really accelerated. So when you're using a 3x3 on a network, it's going to be running super fast as compared to any other kernel. If you're going to be using some other kernel, the whole GPU cannot use the optimized pipeline they are built in for 3x3. It has to use something else, so your network is going to be running slow. So you're going to be seeing in our course that if you're using any other kernel than 3x3, that we're going to be heavily penalizing you. And the reason for that is that we want you to use things which are already state of art, things which actually are optimizing, things which people are using for their own optimized network. We don't want you to use something which is not optimal. Now, I just want to take you through this particular concept. Now, please, let's say we have 400 cross 400 image, which means that we have an image of 400 pixels on x-axis and 400 pixels on y-axis, and we want to go to one number. Why do we need to go to one number? Because we have to see the whole image. Now, let's look at this image again. Let's say this image was about finding a particular digit, and that digit happens to be written here. If that digit is written here, then this pixel does not know anything about that. This pixel does not know anything about that because this pixel just sees these 9 pixels, right? So this pixel will have information only from this particular location. It will not have any information about that location. So if you're not looking at the whole image, you will never be able to talk about what exactly is there in the image. So if I tell you, let's say I'm looking at a leg of an animal, can you tell me what that animal is? You cannot. You need much more information than that. Maybe in some cases you can do that. Maybe you know that that is how a tiger hand looks like, or tiger leg looks like, or that is how elephant's leg look like. But it's not going to be something which can be common in all animals. You might get confused between lion and tiger and maybe similar breeds of such animals. Like in dogs, it's very difficult to figure out what breed it is. Sometimes it is easier, but sometimes may not be. In fact, we can talk about humans. What if I show you a feet of one of the actor in the Bollywood? Can you tell me which actor that is? May not be, but maybe from the physique, maybe from face, definitely you can do that. So what I'm coming at is that you need much more information. You should be able to see the whole image. If you have not seen the whole image, the final guy who's going to be telling us that this is an elephant or a tiger or a cow or Shah Rukh Khan or someone else will not be able to take that call, which means that we have to add layers as long as we do not meet our resolution, and that is where the receptive field concept comes in. Now this guy here, yellow, has seen these 9 pixels. This is called local receptive field. Local receptive field would be the number of pixels you have seen just before your layer. This guy has a local receptive field of 3 cross 3 because it is looking at this channel. But if you open all the windows, it can actually look at the whole 25 pixels here. So the global receptive field here is 25, and that is 5 cross 5 or 25, and that is something you need to remember because we're going to be working on global receptive field concept. Now from here on, whenever we are saying receptive field, we mean global receptive field. When we want to talk about local receptive field, we'll use the word local, but for the global we are going to be skipping that. Now if this is a guy which is going to be taking a call whether in the image of size 400 cross 400 it's a tiger or a lion or something like that, it has to see whole image, which means that we have to add layers as long as we do not meet 400 cross 400 as the receptive field. We need to be close to that number. We can be 398, 399, 401, those numbers are fine, but we have to reach that particular number. Now in the first 4 sessions of EVA, I request you to imagine that every time our deep neural network is looking at any image, the size of the object inside the image is equal to the size of the image, right? I'll repeat that again. Whenever we are looking at any image, or our deep neural network is going to be looking at any image, the size of the object inside that image is going to be equal to the size of the image. It gets clear if you look at this particular image, right? Now in this case, the face is nearly the size of the image, and that's the idea. For first four sessions, please imagine that this is all going to be the case always. After the 4th session, I'm going to be breaking this concept and helping you understand what happens when the size of the object is not equal to the size of the image, which is mostly the case. But until we actually reach those concepts or cover those concepts, please consider this particular fact. So now the problem we were talking about is we have an image of size 400 cross 400. How many layers do we need to add to make sure that we can actually see the whole image, right? Now if we go with our logic, when we start with, let's say, 5 cross 5 and if we add a convolution layer, it becomes 3 cross 3, right? So we have a loss of 2 pixels here. That means that if you start at let's say 49 cross 49 and add a convolution layer, we are going to be getting 47 cross 47, right? And after that we add another one, we are going to be adding we are going to be getting 45 cross 45. So every time we add a layer, there's a loss of 2 pixels, which means that we are going to be starting from 400, then we are going to be getting 398, then we are going to be getting 396, then we are going to be getting 394, and so on, right? Now we can immediately calculate the total number of layers. We have 400 pixels, and every time we lose 2 pixels, so this is going to be giving us 200. This is sort of a fast way, this crude way of calculating how many layers we want. Now so every time we add a layer, we are losing 2 pixels, and because we are losing 2 pixels, the size of the image is becoming smaller, and then finally we get to 200th layer, where finally we have seen the whole image, and that's the idea, right? So please remember this particular concept, the receptive field, that we have to see the whole image if the final layer has to make a call of what exactly the object is all about, right? Now 200 layers is a large number of layers. We have ResNet 54, which is one of the very good architectures. In fact, the state-of-art architecture for object recognition, object detection is DenseNet. It has 121 layers. This 200 layer network is not going to cut ice for us. On our GPU is going to be actually coming out and tell us that our GPU is going to be just coming out and tell us ohm, which is out of memory. We don't want that. We want our GPU to be able to train the network and be able to handle many number of images. So again, concepts we're going to be covering later on, but this is a very, very large number of layers. Now if you think about that, this is 1, this is 3 cross 3, 5 cross 5 and so on. You're actually looking at some sort of pyramid, right? Now if you look at how pyramids look like, I know you know how a pyramid looks like, but believe me, I'm coming to a point here. Now this is how a pyramid looks like, right? These are our pyramids. Now if the aim for us is to reach at the top of the pyramid always, that we start from the base, let's say this is the base for us, we start from some base of 400 cross 400 and finally we want to be at the top, 1 cross 1. Later on I'll tell you that this is not 1 cross 1 but some other number, but let's consider 1 cross 1 for now. Reason we are saying 1 cross 1 is because we want to be at a layer where every pixel has seen the whole image. So this pixel has seen the whole image because the pixel layer before that had seen the layer before that, has seen the layer before that, and so on. And by the time you reach here, you're back at the original image. Now when we add layers like this, we are going to be getting at a stupidly large number of layers, which is 200 here. We want to reduce the number of layers. And if I ask you a question, which other civilization made pyramids, you're going to be telling me what? Mayan pyramids, right? So this is how pyramids look like, and this is how Mayan pyramid looks like, right? So we have steps here, which means that we can actually, if all what we wanted to do was to be on the top of the pyramid, so instead of following that straight line, we can actually break that. We can actually break it, make our image smaller, and then break it and continue adding layer, then again break it and add layer, and break it and add layer, and so on, right? What we're doing here is something like this, right? Let's say we are starting at 400 cross 400, we go to 398, then 396, then 394, then 392, and then 390, and we do something here. So this 390 actually becomes 195. We just reduce it in half. So this particular point is a question for you, that what exactly are we doing here, and how do we make sure that we are not losing information, right? Because we have just reduced the number of pixels to just 25% of pixels we started with. So when that happens, we need to make sure that we are not losing a lot of information. Now for that, I want you to look at this image from some distance. If you're looking at a screen, you've already looked at a screen and you've already looked at everything which is here. But if you're looking at this image from some distance, what you're going to be seeing that you still can talk a lot about that image. You can actually still say that there are humans, there are 2 people, one of them happen to be a woman, there's a small child, there's a green lawn in front of the house. House has a brown color, it has some sort of a triangular structure on top, there's sun, there's cloud, and so on. You might be missing other features, and those features might be these flowers, those features might be this knob, those features might be this chimney and the smoke coming out, those features might be his tie and these pockets, right? So when we are scaling the image down, we might not be able to identify those things. So we might be losing those information, and this is called pooling operation. We're going to be seeing how pooling operation is done. But if you can figure out one way, let's say we wanted to figure out what in this image, we wanted to figure out what woman is wearing and whether what woman is wearing has pockets or not. Now clearly when we have scaled this image down, we are losing a lot of information. So we have the pixels are gone, the amplitude of pixel has also reduced. We need to make sure that we can do something here. And what we can do here is that before we actually apply this particular operation, we can actually take these particular pockets and enlarge them. Now that thing happens by backpropagation. There is a kernel, let's say I told you about kernels, right? A kernel is going to be extracting some feature. So let's say in our network, there is a kernel which is going to be extracting these pockets, because for some reason extracting pockets is an important concept or important tool for our network. So when it is extracting pocket, it extracted a pocket and it passed on the information. But as soon as we did pooling, the information was lost because the information was not able to go forward. That information was not speaking very loud. So what that kernel is going to do, it's going to multiply that same pocket next time with a much larger number. How will the kernel know that it has to multiply with a larger number? That is where the backpropagation will kick in. Backpropagation will change the values of the kernel, and the kernel now will be multiplying with a larger value. And when we multiply it with large value, that feature will become a loud feature and will automatically pass on. Now the particular algorithm we are talking about here is called max pooling. Now you're seeing a 6x6 image. In this image we have we're doing a 3x3 max pooling. We never do 3x3 max pooling. We always do 2x2 max pooling. Now but when we are doing 3x3 max pooling, you see that in the first 9 digits this is the largest digit, in the second 9 digits this is the largest digit, and 3 and 7 so on. So if we were to do actually, let's say, max pooling of 2 cross 2, which is what we do, from the first 4 digits we are going to be getting 5, then we are going to be getting 6, then we are going to be getting 4. From the bottom, from the middle layer, we are going to be getting 9, and then we are going to be getting 7. After that, we are going to be getting 5. Then we will get 3, then 3, and then 5. Right? That's a max pooling operation using a max pooling of 2 cross 2. We always use 2 cross 2. Now this is 6 cross 6. This is 3 cross 3. 6 cross 6 has 36 digits. 3 cross 3 has 9 digits. We have lost 25% of information here. When we are using 3 cross 3, we are going to 4 cross 4 directly from 36, right? And this is a huge loss. This is something which we cannot handle. And when you do a max pooling of 3 cross 3, you're going to be losing a lot of information. So there has to be a very, very specific use case why you might be using that. We'll share some ideas later on, but for now, please tell yourself that you never, ever, ever use 3 cross 3 max pooling. We always use 2 cross 2 max pooling. Now, just look at these numbers. Now, let's look at these numbers. We have -4, 5, 5, and -4. So we take the largest number out and we just pass on that number. So in our case, we have taken 5 out. In this case, we have 0, 9, -1, -3. What are these numbers? These numbers are the 9 multiplication and sum of our kernel convolving on the layer before that. Right? Now, when that happens, imagine that the kernel was on top of the pocket. It multiplied with those numbers and it generated a digit. Let's look at some close numbers. Yeah, let's look at these numbers, right? -4, 3, and 0, and 7. So our kernel did multiply on top of the pocket. It did identify our pocket, which was 3, but there is some other feature which actually got ahead of that at that particular pocket. And that is something which is not good for a network. Our accuracy will not be there. We are not detecting the pocket. So next time when a deep neural network or backpropagation happens, this 3 number is going to be changed. This 3 number will become 3.1, 3.2. These numbers change very slowly. And this 7 will also reduce, because not only increasing this is a good idea, reducing this also a good idea. So 3 is going to increase and 7 is going to reduce, as long as finally whatever is here is not passed on in the max pooling layer. So this is how max pooling layer is going to be working or helping us reduce the number of channels, and this is how backpropagation is going to be making sure that when we are using max pooling, only those features are going forward which are loud, and a backpropagation will make sure the features which are important are always loud. So another idea, another good example would be, let's say we are writing a face recognition algorithm, and that algorithm, I have a twin brother, and I'm asking you to just imagine. So I have a twin brother, and imagine that deep neural network is supposed to identify both of us. And I have a mole on my cheek, but my brother does not have a mole on cheek. So network might learn that as whenever there's a mole on the right cheek, it is Rohan, otherwise it is not. But because of max pooling, that kernel which learned the mole will not be able to pass on that information. So next time, backpropagation is going to take that mole and increase the size of the mole. When you increase the size of the mole, in that case, when a kernel is going to be convolving, it will be able to pass on that particular information. So that is how backpropagation and max pooling and other layers are going to be working together. Right? Now let's go back to our problem here, which is how many layers do we need to add? Right? So in this case, we know what this question mark is. This is called max pooling. Right, so from 195 we go to 193, then we go to 191, then we go to 189, then we go to 187, then we go to 185, and then we again do max pooling. Right, now the reason we are adding max pooling layer here and not before is something which is slightly tricky to understand, so I'll be able to explain that in the next session. But to give you a pointer, remember I told you that first we extract edges and gradients. So by 390 we need to make sure that we have actually extracted edges and gradients, and that is when we are going to be adding max pooling. Why does it happen at 390 is something we need to discuss later on, but this is exactly where we want our edges and gradients to actually work out. This is a large image, so we will have edges and gradients and textures and patterns and parts of objects and so on, right? So right now we are looking at complex textures. So if we have done max pooling here, we're looking at complex textures. Okay, so when we do max pooling of 185, you are either going to be getting 892 or you're going to be getting 923. Now that depends on whether you want to add zeros all along 185 rows and columns and make it 186, or you want to reduce or not take care of the last row and column. Both are fine. You are not losing really a lot of information. If most of the information for you happens to be on the last row and column of the image, you're already doomed, because we have to have most of the information in the center of the image. Remember, we are talking about our size of the object being equal to the size of the image right now. Later on we are going to be talking about how do we handle the border cases, but right now it's not going to matter a lot. So from 82 we are going to be going at 80. Remember, every time I'm adding this pipe, we have added a 3x3 convolution layer. Then we are going to be going at 78. Then this is going to be 76. Then this is going to be 74. Then this is going to be 72. And let's say we are at 70, and now we do max pooling again. Now when we are doing, we are making patterns. Once we have done, once we are here, we are going to be at 35, then 33, then 31, then 29, then we are at 27, then we are at, let's say, 25, and let's say we do max pooling again. Here we are making parts of objects. Now we are at 12, we then go to 10, we go to 8, then 6, 4, 2, and 2 or 1, right? How do we handle that? Again, we are going to be discussing that later on, but just now imagine this is the sequence of how things have happened. Now here what have we made? We have made objects. So this is important. We add max pooling layers exactly where we are sure the edges and gradients are made, then where the textures are being made, then where the patterns are being made in parts of objects, and so on. This is true only if the size of the object is equal to the size of the image, and that is why I'm insisting that for the initial few sessions, please consider that that is the case. Now in this case, we've added 1, 2, 3, 4, 5, 6. Then this has 6, and this has, I believe, 7. This has 6, and this has 6. Now quickly, like 6 into 5 is 30 plus 1, so, right? We have used 31 layers. So instead of 200 layers, we have just used 31 layers. Lot less number of layers, lot less number of parameters. That is how we define a particular deep neural network. That is how we write a deep neural network, right? The important concept here is that we have to start from 400 and we have to end here. Whenever you're adding a max pooling layer, our receptive field is getting doubled. So that is very important. Now because our receptive field becomes double, we are still making sure that we are actually looking at the whole image, right? When we are doing something like this, we are actually looking at the whole image. So it's very, very important for you to understand, right? Okay. Now let's go to the assignments now. Now we have two assignments. You're going to be uploading one folder on your GitHub repository called Project One. In that, you're going to be adding a particular code. When you click on this particular link, you're going to be seeing this particular page. Now in this page, I've written an OpenCV code. Here we are opening one particular image, and this is Canny. Just for fun, I've just added it here. This is important. We have written this particular kernel which is able to extract vertical edges. Now what you're seeing here are some of the edges which are combined together. Now because these edges are small, you will have many repeated vertical edges here, right? You see this W, you have many repeating vertical edges here. So this particular kernel does something like that. What I want you to do is to figure out these values manually in such a way that you can actually detect a horizontal edge or an edge at 45 degree on the either side. It might be left starting or right starting edge. I want you to figure out how a blur kernel can be written. I wanted to figure out how a sharpen kernel can be written. If you can think how to blur an image, I wanted to think how can you sharpen an image, and I wanted to figure out how identity function can be written using these using the 3x3 kernel. Now, what is identity function? Identity function will be a function where you're going to be writing these 9 values in such a way that you start with this image and you end with this image. It does not do anything. It's a very important function we'll realize later on. Some instructions, you can only use a 3x3 kernel. Do this on Colab, because otherwise you have to figure out how to install OpenCV, Python issues, and Anaconda, and different path issues might crop in. We don't want to spend time there. So just do this on Colab. Once you're done on Colab, copy that file to your GitHub. We should be able to look at your file and comments on the GitHub project link. We'll not be looking at the Colab link, but we request you to add that as well, because in case for the initial few sessions you are missing, you're not able to import the files properly, we can go and look at your Colab files. Now 50 marks is for the correct code and 50 marks is for the great documentation. How will you write the code? You're going to be, this is one block, right? This is the vertical edge block. You're going to be adding a new block, and you will be describing how the horizontal kernel can be made. After that, you're going to be adding another block where you're going to be showing 45 degree block and so on, right? So we need to show you need to show all the images and all the outputs of your kernels. Now in the assignment 1B, in the same project folder, we want you to add a readme file called as assignment 1B, and I want you to answer these 3 questions. What are channels and kernels according to EVA? So this is based on what we are discussing together, right? You can go online and search for different topics, but I really want to know what do you understand what channels and kernels are based on this particular session. Now, why should we only use 3x3 kernel? I'm using the word I'm using the construct mostly because later on you will see that there are small exceptions to this, but those exceptions are really very well defined. So we can actually, by swear, we can actually swear that we always use a 3x3 kernel. So my question to you is that why do we always use 3x3 kernel? This question is how many times do we need to perform 3x3 convolution operation to reach 1x1? I want you to do the similar calculation what I've done here, but you're not expected to use max pooling. You cannot use max pooling here, right? So you'll be showing 199, then 197, then 195, then 193, then 191, and so on. I want you to manually write this, and the reason I want you to manually write this is because this is boring, and then you will realize that why max pooling is actually required. Unless you feel the need of max pooling, you will not actually know that max pooling layers might be required, because right now you'll not be working with large data sets, so your program will run faster even if you're not using max pooling. But by the time you hit any complicated assignment, which will start immediately from session 3, you'll see that you're going to be going out of memory. So we need to get into a habit of actually using max pooling layers, and habits are very difficult to create, right? Unless you go through some sort of pain, you do not learn that specific topic. So this is my way of giving you some pain. Again, 50 marks for your explanation and 50 marks for your creativity. Now, what do I mean by creativity? You know what is creativity, right? So I want you to show all of this in a very beautiful way, in a way in which a student can actually look at your explanation and understand that. Maybe you can add image, maybe you can draw some image and upload that image yourself. You can think, how do you get this additional 50 marks? Now you're going to be uploading your GitHub project link to the LMS. It is already up if you're seeing this video. Our deadline is 1 hour before next session. You must use your own words. We have a plagiarism finder, so we'll go online and we'll try to search whether you have used the same words from online or not, so please don't do that. So yeah, that's about it. So if you have any question, you can post on the LMS discussion page. Thank you.